So first we will talk about the pressure versus volume diagram of the diesel engine. So this one is the diesel engine. So first you should notice that I should tell the differences between petrol engine and the diesel engine. The first difference is that in petrol engines we have used in petrol engines you are using the homogeneous mixture of the fuel and the air. But in diesel engines you will use, so that diesel engines, it uses air. Okay, it compresses air firstly. Okay, it's compressed, and then after that, after you reach some temperature, okay, after you reach the sufficient temperature that it is okay for the auto ignition of the diesel, and then you add the diesel. Okay. The first you compress the air. Okay, diesel engines first they compress air. Okay. Let me add this one. Use air separately. It isn't the diesel engines do not use the air as a part of as a part of the fuel. It is not a homogeneous mixture, but first you compress the air, and after you reach some temperature, so that you reach that temperature, that this temperature is enough for, so that it is auto ignition temperature of the diesel. And then when you add the diesel, at that stage, you are not adding the diesel in liquid form, but you are adding diesel as the sprays. Okay? And you are adding the diesel as sprays. And then when you add the diesel as a spray form, it will, since it is auto ignition temperature, the diesel will burn, and you have the combustion stage as well as the power stage. Okay? This is the main important difference between the diesel engines and the petrol engines. And the second one is that in the second one, I've told in the first one that the diesel engines, you can see here, it uses compression. Okay, it doesn't use any spark plug. So here you don't have any spark plug. Okay, you don't need any spark plug here. Okay? This is another main difference between the diesel engines and the petrol engines. And the one more important difference between the diesel and the petrol engines is the compression ratio. If you remember it was the maximum volume and divided by the minimum volume. Okay. For diesel engines, this compression ratio is about that 18 to 22. But if you remember, for the petrol engines, it's about the 8.5 to 12. Since the compression ratio for diesel engines is very large, that compression ratio means that this large amount of the compression ratio means that you have that what is called, you have a bulky system. Okay? Therefore, the diesel engines are bulky. They are very large. Okay, but for the petrol engines, the compression ratio is small, and therefore the engine itself is small, because the volume means that the space that it holds, and therefore the petrol engines is not so large as the diesel engines. But we have said in our last lecture, this high amount of the compression ratio gives high torque to the diesel engines. That high torque is used for heavy trucks. For example, if you have the bus or the train, all of them, the heavy trucks use the diesel engines. So these are the main important difference, but this compression part is the one that is most important. And therefore, the diesel engines are called that CI engine. Okay? CI means that compression ignition. The ignition happens by compression, but this one's for the petrol engine. Petrol engines are called SI engines because here you have this, that is spark ignition for the diesel engines. These are the main important difference between diesel and the petrol engines. Now you can see the animation of it. Let's have a look at it. So again, this one is the 4-stroke diesel engine. So I will increase the speed a bit. So you will have the 4 stages, 4 strokes. You can see. And now you will have the intake. So, but for you can see that for the intake stage of the diesel, okay, it happens at the top dead center, because after you have the enough amount of the compression, you have the addition of the fuel. You have the compression. You can see the names of let me increase speed a little bit. You can see the names of the stages here. Now it is exhaust stage. You can see it is exhaust. Now the combusted products are leaving. You have the intake, but intake here you have the air only. Okay, it is not the fuel, it is air. And then you have the compression. After you reach enough amount of the compression, you can see that. So now you have increasing. You can see the value of the pressure, and the pressure value, it increases. And at the top value, the peak value, you will now you will have the fuel. Okay, now you can see that fuel is added now. And then you have the power stroke. You have the power stroke now. The engine goes. And then at the end of the power stroke, you are reaching next stroke, which is the exhaust. And the exhaust stroke, all of the gases will leave the system. Okay, all of the combusted products, and the cycle goes on and on. Okay, this is the diesel engine. You can see the efficiency, it is 86%, 56% efficiency, but it is not the realistic efficiency. Okay, this one is the ideal one. Okay. And the power is 17.46 kilowatts. Okay. So I should say this one, in reality, it is around the 30.5%. Compression ratio, you can see it is very high. And then cutoff, there's also cutoff ratio. I will talk about this one. And the maximum temperature, you can see it is 1823 Kelvin. And these are the stroke diameters, the stroke lengths, and this is the bore diameter. The bore is the diameter of the piston, and the stroke is the distance that is traveled between the maximum volume and the minimum volume. Okay. And this one is the displacement volume. Okay, this is the diesel engine, and you can look also for the pressure versus the theta diagram, which is the angle of the change of this crankshaft here. You will have 720 degrees because you have two full revolutions. Okay. We have talked about this one in Otto cycle. Now the pressure will increase from this angle. You'll have then the fuel input, and you have the power. You can also have the temperature versus theta diagram and the temperature versus entropy diagram. Okay, this is the diesel engine. Now I will talk about the real cycle of the diesel engine. Diesel engine, it's also called the indicator diagram. In the real cycle, you can see the differences between the petrol and the diesel engines. The first, so you have the compression stroke, it is on the way, it is not the problem. So you have 1 to 2, let's say. You have the compression. This one is the real one. Okay. And then you have the 2 and the 3, you can see it. You have that is the combustion. You have it here. And then 3 to 4. And actually from the 2 and the 3, you have also the expansion, because you can see it is the directions in that way. Okay, from 2 and the 3, the volume increases. And since the volume is increasing, it is also the combustion as well as the expansion stroke. We can put some 2 prime here, the 2 prime. And then you will have that from the 3 prime to this amount, you will have that expansion. This one is also expansion. Okay, I should note it. This one is also expansion. Combustion is a process, but it is expansion process. Here you have that change of volume from the 2 and the 3 prime. You have the change of volume. Since the volume changes, so it is expansion process, because at the end you have P delta V, PdV. Okay. Since dV is positive, then you have the expansion stroke. And then from that 3 to 4, this stage here, okay, 3 to 4, you have the blow down stage. This blow down, it is not a separate part of that engine, but you should know that this one is very important. Okay, 4 prime, let's put it. It is very important process. Why it is very important? Because at this blow down process, you don't have any volume change. Volume is approximately constant. but the pressure drops. You can see it from 3 to 4 prime, the volume change, dV is 0, but the P drops. So what it means is that with that pressure, you could do some useful work, but you cannot do it due to the volume changes 0. So you have the losses here. It happens in diesel auto engine too. I've talked about that one. In auto engine, the petrol engine, you have also blow down process. Okay, it is the real stuff. In that blow down process, so that the pressure suddenly drops because here you have the exhaust valve open. Okay. And the exhaust valve open means that the pressure suddenly drops. But this drop of pressure happens suddenly, abruptly. There is no change in volume, and then PDV work is 0. And that PDV work is 0 since PDV is 0 because the dV is 0. So you can do some useful amount of work with the pressure change, but you cannot do it. Therefore, this is losses. And then from 4 prime to that point, let's say that this one is that A. Okay. And from 4 prime to A, you will have that exhaust stroke. Okay. And then from A to 1, you will have intake. How do I know that this one is intake and this one is exhaust? You can see if I take this one as a PATM, okay, for the exhaust, it should be larger than PATM. So this one, you should have pressure that is larger than 1 atm because otherwise the combusted products cannot leave the system. So here you should have the PATM so that combusted products leaves. But in the next stage, where it goes from A to 1, so you should have the intake. Intake means that the pressure should be small, less than PATM. Otherwise, the products that cannot enter the system. Okay, the system should have the pressure that is less than 1 atm, the atmospheric surrounding pressure, so that the gases can enter the system. That is the pressure versus the volume for the real one. This is the real. Now, what we are doing is that in thermodynamics, we are approximating this diagram with some ideal processes and trying to understand what happens in reality. Because reality is very complex. It's not difficult. It is not very easy to understand the real processes because here you have the three-dimensional effects, you have the turbulence. Therefore, that we are trying to understand the process in thermodynamic way, and then to understand it, so firstly what we will do is that we will also here have the same process as that petrol engine. You have the compression stroke. Let me start somewhere around here. You have the compression stroke from 1 to 2. Okay, but from 2 and 3, this is the main difference between the petrol engine and the diesel engine. For petrol engine, let me write this one to here. Here, combustion happens at constant pressure. For the diesel engine, combustion happens at constant pressure. For the petrol engine, but you can see that combustion happens at constant volume. It is almost constant. That is the main difference between the petrol and the diesel engines. For the petrol engines, it happens suddenly, and therefore the volume change is approximately 0. But for the diesel engines, these are a bit lazy, okay, because the process happens very slowly due to high amount of compression ratio. Therefore, this combustion process happens at constant pressure, and you have the volume change, time for volume change. And therefore, you will have the 2 and the 3. This one will be that. Now, in this process, we are saying that instead of that combustion, you have the QE. And from that 3 to 4, you will have that. You will have the, I'll put it here, expansion process. Here you will have the expansion process. 3 to 4. Let me correct this chart a bit more. So you will have the heat addition process from the 3 to 4 here, heat addition, and then you will have that expansion process here. This one is the expansion, okay, same as here. Okay, here you have the expansion stroke, or it is power stroke. And the fourth one, you should that complete this cycle, but here you have the constant. Here you have the constant amount of the, you have the heat addition at constant volume. Here you will have the heat addition at constant volume, but you should mix, you should intersect with the point 1 here. Let me draw it one more line here. Okay. This one is the point 1, and this one is the next stage, and this one is the compression. And here you have the Q out. This is the diesel engine. Diesel engine is like this one. You have the heat addition, you have the expansion, you have the Q out at constant volume, and then you have the compression stroke. Okay. You can see that Q out at constant volume. And as we have said in our last lecture, this part where you have the intake and the exhaust strokes, these works cancel out because one is this is approximately symmetrical. Okay. And since it is approximately symmetrical, the positive part cancels out the negative part. You don't have any work output, approximately. Okay. Good. So we have it. And then now we will do a simple example. Then this one is the diesel cycle. Now the example is that we have a diesel cycle with a compression ratio of 18 and the cutoff ratio of 1.8. Is running with inlet air pressure and the temperature values of 1 bar and 30 degrees Celsius respectively. Accounting for the variation of the specific heat values, this one is very important, find the temperature of the combustion process and the efficiency and the map of the cycle. And who remembers what was the map of the cycle? Who remembers it? What is map? Nobody. What is map? Map is mean effective pressure. Mean effective pressure. The map is the mean effective pressure. Okay, now let's solve the problem. So firstly, we have the compression ratio. This compression ratio, CR, it was the maximum volume divided by the minimum volume. Or you can say that the maximum nu divided by the minimum nu. Okay. If it is this is closed system, you can see this closed system, and the mass is constant here. And since the mass is constant, you will have this nu. It doesn't matter nu max divided by nu minimum because that mass is constant here. And for this one, the maximum volume is at 1/4. This is the maximum volume, and the minimum volume is at 2. Therefore, you will have that nu1 or nu4 or nu1. This is the maximum volume, and this one divided by the minimum volume, which is nu2. This is the compression ratio, and you have also that cutoff ratio. This is also important, cutoff ratio. And the cutoff ratio is the ratio between the combustion process ends, which is the 3, and the combustion process starts, which is 2. You will have that nu3 divided by nu2, which is the cutoff ratio. It shows the ratio of the work done. Okay, so that work done between 2 and the 3. Okay, so in our case, that combustion ratio between 4 and the 2 is 18, and cutoff ratio between 3 and the 2 is 1.8. Now, what will I do is that I will draw a table here to see which values do I know and which values are unknown. And I will use also Gibbs phase rule, which says that you have to know 2 independent intensive properties to find any third one. Now, let's do it. Okay, so you will have that pressure, temperature, and nu, and internal energy, and also entropy. This is also important for this cycle. Okay, and you also have this entropy. Yes, but for the difference between the real and the diesel cycle is that Let me add it here. For diesel cycle, which is the thermodynamic cycle, and the 2 and the 1, 3 and the 4, I've said in the Otto cycle, these expansion and the compression processes are, that is, frictionless, and they are adiabatic. And the processes 2 and the 1, from 3 to 4, okay, they are frictionless and plus adiabatic. This is very important for our case. Now let's write the values now, what the given values. The pressure, the firstly that we have 1, you have 2, and the 3, and you have the 4. These are the states that we have for this cycle. And for the first part, where you have the start of the compression stroke as well as the cycle, the values are given. You know the pressure, which is 1 bar, and you know the temperature, which is 30 degrees Celsius. Therefore, the pressure here will be 10 to the 5 Pascal, and then the temperature will be here at 30 degrees Celsius. And also we know the ratios of that nu4 to nu2 and the cutoff ratio. And if you remember that Gibbs phase rule, and the Gibbs phase rule says that you have to know 2 intensive independent properties. 2 intensive independent. Okay, we have to know it. If we know it, we can find any third property, any of it, we can find it. Now let's get the values. So for the first stage, where you have the pressure and the temperature, the specific volume value, we can find it because we know 2 properties here. So the third one, we can find it. We can find internal energy because we know these values here, and you can also find the entropy. It is okay. Now comes the second stage, stage 2, where it goes from 1 to 2. And from 1 to 2, we have said that it is frictionless and adiabatic. If it is frictionless and adiabatic at the same time, and it is also isentropic. If the process is frictionless and adiabatic, it is isentropic. Therefore, entropy of 1 will be the same as entropy of the 2. So I can write this one as entropy of 2 is same as entropy of 1. Okay, good. And I know also the ratios of the specific volumes, because that is given as compression ratio, which is 18. And therefore, that nu at stage 2 will be that nu at stage 1 divided by 18. You can now see it. I know 2 properties, which is entropy and the specific volume. Therefore, I can find any third property. Therefore, this one is known, this one is known, this one is known. 2 important properties are found. Now comes that state 3. For state 3, let's have a look at which values do we know. Okay. State 3 is end of the combustion process, and from the chart you can see that the pressure at 2 is same as pressure at 3. So here you have the same pressure at 2. Therefore, we have 1 Gibbs phase rule. It says that 2 intensive properties. 1 is okay. I have found it. Now comes that second value that I need to find any third one. For that one, let's have a look at here. I know that cutoff ratio, because the nu3 and the nu2 is given in the question. This is cutoff ratio. This one is given. Therefore, that specific volume at 3 will be equal to that 1.8 multiplied with the specific volume at 2. Okay. Therefore, I know 2 intensive independent properties. Any of the third one, I can find it. Good. Now comes that state 4, which is the last state. For that state 4, let's have a look at which values do I know. For state 4, that I know that specific volume at 1 is same as specific volume at 4. And the specific volume 1 is same as 4. Therefore, this one will have a specific volume which is same as 1. And also, from process 3 to 4, this is isentropic process. Okay. So this is frictionless, which is expansion process, and adiabatic. Isentropic process, therefore entropy at 3 will be same as entropy at 4. So I will write that here. 3 will be same as entropy at 4. Therefore, this stage is found. There's a different color here. This one is found, this one is found, this one is found. You can see I have found all of the values. All of the values, any value that is not written here, any value you can find it. Because Gibbs phase rule says that two intensive independent properties, if they are known, any of the third property can be found. Now let's solve the problem. The question says that accounting for the variation of the specific heat values. Now I should add one more thing here, is that for this one is the real cycle. For the real cycle, you are using fuel and air combination. Okay. But the diesel cycle, which is the engineering cycle, in this cycle you have only air. The fuel is not considered, only air is considered. This is the real cycle. Then now let's find we have to use the table for the entropy values and the entropy of the change of pure substances, and I'm not looking for the incompressible ones, I'm looking for the ideal ones, okay? And from that ideal ones, you should have the constant specific heats or the variable specific heat. The question says that consider variation of specific heat values, and then you go to that, okay? And here I can find the entropy change by the table, okay? Or I can use that, if it is isentropic case, I can use that three equations here. If you are interested in the entropy change, you can use this part. If you are interested in isentropic case, you can use this part. But for our question, it's all about isentropic processes. Here you have the same entropy. Therefore, I'm not interested in the first part. So I will look for that isentropic processes. Here where you have the constant amount of the entropy. Okay, so I will solve that first parts of the question, because the rest will be the similar steps. I don't want to lose the time, but you can feel how will I solve it. So now let's go to the chart here, the tables, and I'm looking for the table for ideal gas as air, which is table A17. Let's go to table A17. Okay, for table A17, you have that temperature, which is that 30 degrees Celsius, and you should remember that for ideal gases, that internal energy and the enthalpy is function of temperature only. Okay. And that for that 30 degrees Celsius, which makes 303 Kelvin. Okay. So you can look at it, you don't have that temperature, you can use interpolation. I will show how to use interpolation, but I will not use interpolation. I will take approximate values. So temperature value, which is that 300 Kelvin. So this one is the internal energy and this one is the temperature. You have that 300 Kelvin here, and you have that 305 Kelvin here. For that 300 Kelvin, you have that internal energy value. For this one, internal energy value is 214.07. Okay, 214.07. This one has a unit of kilojoules per kilogram. Okay. This one has a unit of Kelvin. For that 305 Kelvin, you have internal energy of 217.67. Here you have 217.67. Okay. This is the internal energy for the next temperature. Okay. And in between these temperature values, from that point to this point, you will have the linear change. And then for that linear change, what we are trying to find is that we are trying to find the temperature at 303 Kelvin. Yes, I'm looking for the temperature value approximately here. Okay. what we will do is that this is unknown. Okay, so let's say that this is U that I'm looking for. The differences between these and internal energy values, 1767 minus 1407, divided by the difference between these extreme values, 305 minus 300. That should be equal to the differences between this internal energy value with that one or with this one. It doesn't matter. You can take any of it. It will be U minus 214.07 and divide by the same temperature value, which is 303 minus the same for the other internal energy. And from here, you can find the internal energy value. Okay, you can use the interpolation, but I will not use interpolation for this problem, but I will use approximate values for saving time. Okay. Now let's go back to the chart here. You can see it goes one by one, so it will be about 216. Sorry, 216. So you will have that 116 approximately. Okay, you can work out the exact values. And then you have to look for the specific volume value, which is nu, and this nu value you can get it from the ideal gas relationship, because P nu is RT. Okay? And temperature value is 303 Kelvin, and the R value is 287. Pressure is 10 to the power of 5, and from here you can get the value of the nu. Okay? This is for the first stage. Now comes the second stage. And since you have volume divided by 18 will give you the specific volume for 0.2. Okay, and now entropy value, which is the difficult part for you, and now let's solve the entropy for state 2. S2 divided by S1. Okay. For that entropy ratios, you can work. You can see that 3 formulas here. Okay. You can work out with that nu2 by. This one is not S2 by S1. For that entropy relationship, isentropic relationships, you can use that P2 by P1, PR2 by P1, or you can use nu2 by nu1, nu2 by nu1. Any of it is okay, but I will use this one. But you can use this one too, it doesn't matter. Then you will get the same values. Okay, so that, therefore, I should find that P2 by P1 will be the same as PR2 by PR1. Let's use it. If it is okay, then we will be fine. So the problem here is that we can see it. P2 is unknown. Okay. Since P2 is unknown, PR2 will be unknown because temperatures are not okay here. This one is function of temperature. Since I don't know the temperature, I don't know PR2, and I don't know also the P2 value. Okay, so these two are unknown, P2 and the PR2. Therefore, this formula is not okay. So let's go back to the next formula. That next formula is nu2 by nu1 is nu R2 by nu1. Let's write that one. Nu2 by nu1 will be the same as nu R2 by nu R1. Okay. This is the second formula. Okay. For that formula, I know the nu2 by nu1. This is okay. And nu R1, I can find it from the chart because it is the function of the temperature only. From here, I will get the nu R2. Let's do that. Nu R2 will be equal to nu R1 multiplied with nu2 by nu1. Okay. And nu2 by nu1 is 18. Sorry, 1 by 18. It's given in the question. It's a compression ratio. So this ratio here is 1 by 18. And nu R1 value, this one is from the chart. Let's go back to the chart here. You can see that 303 Kelvin here, you have the nu R values. Okay, nu R values you can have here. So both nu R values. And then what we are looking is that we are looking for 303 Kelvin. You can see that it decreases about 1 by 1. So therefore you will have that 618 approximately. 618. And there is no dimension here. You can see it is dimensionless quantity. It doesn't have any dimension. Okay, so I have this one and I have that ratio, and from here I will find nu R2. And if you solve it for the nu R2 value, you will get, give it a value for this one because it's required for the next stage. It is 34. This is the nu R2. Okay, since you know the nu R2, this one is okay. Now let's go back to the chart again. Nu R2 value is 34. Let's go back to the chart. And then from that chart, you can see for 34 of new R value, you can see new R. For that value, you have all of the temperature values, internal energy values. You can get it. Okay, it is 1 to 1. So therefore, for that new R value, you will have 900 Kelvin temperature. The temperature here, T2 is 900 Kelvin. And as well as the internal energy at 2 is, so let me see that which one is internal energy. This one is the 674, 75 kilojoules per kilometer, approximately. Okay, so therefore, for stage 2, I have found that temperature value, I know it, I know that internal energy value, and I can find the new 1 value because new 2 value because new 1 value is okay from the ideal gas relationship. And if you solve that equation, you will have that. Okay. So 0.87, and this one will be 0.87 divided by 18. And you will have that 0.04. Let me write in different color. Okay, 0.04. Okay, so you have the new 2 value, you have that temperature values, pressure values, you can find it from ideal gas relationship. Okay, so if you have any questions, you can ask. Is there any question? Is there any question? Okay, so then. So you have that second stage is okay. By using the ideal gas relationship, you can find the pressure at 2. The pressure at 2 will be nu 2 will be R into temperature 2. From here, you can find that P2 will be equal to R is 287, temperature is 900, and divided by that nu 2 value, which was 0.04. Okay. And from here, you can get the values. So if you have the value, you can tell me. So I will wait for your values, okay, so that you can write as a comment, so I can see your values for this one. Okay, so you can write your value for the pressure. I will write it for the second stage. Okay, for the third stage, this is the version. So tell me your values. Okay, I will write it and then continue to next part. Okay, so who has the value? That 640. So you will have that 645, 7500. Okay, this is, so yeah, 1 3 here and 6 megapascals approximately. Okay, for that stage 2. Okay, so that stage 2, we have found it. For that state 3, the pressures are the same. You have the same pressure, and the specific volume values, this one will be 1.58 multiplied with nu 2. Okay, so therefore I can find that P3 is same as P2. That's for stage 3, and then nu 3 will be equal to 1.8 multiplied with nu 2. Okay. And I know that nu 2 value is 0.04. Therefore, 1.8 multiplied with 0.04. And then you will have that nu 3 value. So who has the value for the nu 3? So you should divide that 287 multiplied with 900 divided by 0.04. So that is for the pressure at point 2. Okay, so 0.072. So this one is the meter cubes per kilogram. You have the pressure, you have the specific volume, and since it is ideal gas, you will have P3, and nu3 will be equal to R and the temperature into 3. So from here, you can find the temperature at point 3. It will be that P3 nu3 divided by R. And this one is that if there is no any error, this is the temperature pressure value, and multiplied with the specific volume and divided by 287. Okay. What's the temperature value here? Who has the value? So you will have the, again, ideal gas relationships, and you can find the temperature values here. Okay, so 1620. This is the temperature value for state 3. So since I know the temperature value, then I will go to the chart and find the any value that I need. And for this case, it is the internal energy that I will need, 620. So internal energy value is, you can write it here, so that U3 will be equal to internal energy value 16.96 kilojoules per kilogram. Okay. And I have done the state 3. Now comes the last state, which is state 4. State 4 says that nu1 is same as nu4. So therefore, no need to. Nu1 was 0.87. So nu4 will be same as nu1. It's 0.87 meter cubes per kilogram. This is for nu1, nu4. And it also says that it is isentropic. And the 3 and the 4, you have isentropic relations, okay, between 3 and the 4. And for that isentropic relationships, I can use the formula here. You can see mu specific volume ratios. And since I'm looking for the states 3 and the 4, they are isentropic. They are in isentropic relations. Therefore, I will write that. I can write the formula here. Nu4 divided by nu3 will be equal to nu4 R divided by nu3R. Okay. And then this one is 0.87. I have found it. And the nu3 value is, should be somewhere around here. Nu3, yes, 0.072. Okay. And nu3R value, this one is, let me see, nu3R value. Now I should go to the chart, and with that temperature value, I should find that nu3R. Let's go back to the chart. And for that chart, for this temperature, nu-R value is 5.574. 5.574. Okay. And therefore, you can find nu4R value here. Okay. And do you have the result? You can tell me the result here. What is that result? And then with that result, you are going to find, we are finalizing actually the process. Okay, nu4R. So that it is 67.35. Najmuddin Yaqub. Okay, so now I'm going back to chart again, and using with this value, I will find the temperature. Okay, again I will use table A18. Let's go back to here, and 64.35. I will use again approximate values because I don't want to lose the time. But if you are interested, you can get the real values. Okay, 67.08 0.07, it is 701 Kelvin. So temperature is 701 Kelvin. This is the T4, and therefore I can find U4 value too. And U4 value for the temperature is, so let's see which column I'm looking for. This column, 520. So 520.23 kilojoules per kilogram. This is the U4. So I know the temperature, I know the internal energy. I'm also interested for the pressure value. You can find it. Pressure at 4, mu at 4 will be equal to R, and the temperature at 4. From here, you can find that pressure at 4 will be equal to 287 multiplied with 710 and divided by the new 4 value, which is 5.57, sorry, new R value. New R value will be equal to new 4 value, which is 0.87. Okay, and from here you can get the pressure at state 4. So if you have the pressure values, you can tell me. Pressure values. So that 234, you have 218. So that Abbas and the Yaqub, you have different answers. I don't know which who is right. I will take first value. Okay, then okay, no problem, dear friend. So this is the pressure at 4. Okay, so I have found the pressure at 4. I have found all of the states. Okay, you can see all of the states have been found by simply using Gibbs phase rule. Okay, so this phase rule is very important. You will see that in next cycles, we will only need Gibbs phase rule. Okay, only. Okay, so I have found it. Now let's go back to the question. It says that find the temperature after combustion process. Okay, the combustion ends here, T3, and the temperature at point 3, I have found it, which is this one. Okay, so that's okay. I've done the first part. Find the efficiency of the cycle. Okay, let's do that. So the efficiency of the cycle will be equal to, and this one is the heat engine. If you remember from that thermodynamics one, the heat engine efficiency was work net out divided by Q in. This was what we are doing in thermodynamics 1. If you remember, we have said that if you have a heat engine, you have the reservoir here, and you have the Q in, and you have the work out, and you have the Q out, and you have this one here, reservoir. Okay. This one is the temperature at high, this one is temperature at low, and the Q in is by fuel. Now let's do that for our case. That work net out here will be equal to work of expansion process minus work of compression process, and divide by Q in. Okay, and the work of expansion process, now let's go back to the chart here. Work of expansion process is internal energy at 4 minus internal energy at 3. Compression process will be internal energy of U2 minus internal energy of 1. Okay, that is the application of the first law. If you write the first law, I will write only for expansion part, but you should know that the compression is exactly the same for expansion. You will have the change of internal energy of the system will be equal to total in minus total out. And we have said that expansion is frictionless and adiabatic. Okay, and since it is adiabatic, Q is 0. There cannot be heat transfer by this system. And second, this one is a closed system. So the closed means that mass transfer is 0. Okay. Since it is expansion process, work in cannot be, and there should be work out. Okay. And from here, you can find that work out of the system, which will be -1, will be equal to and change of state of the system. And that change will be second state, which is the U4 minus U3. Let me do that. It will be negative U4 minus U3. And from here, work out will be equal to U3 minus U4. This is the work out. And now for the work in, if you write the first law for work in or compression, and you will get the same the logic here. In that case, your work in will be equal to, again, delta U of the system, and delta U of the system will be from 2 minus 1. So U2 minus U1 will be U2 minus U1. Okay. Now let's write the values and calculate these ones. You will calculate by yourself. Let me write the Q into, so that first law for combustion. Okay. If you write the first law for the combustion process of the diesel engine, so that internal energy change, so let me write it, delta U of the system will be equal to total in minus total out. Okay. And for the combustion process, you don't have, so let me go back to the combustion process here. From the 2 and the 3, this is the combustion process. Okay. But in that combustion process, you have also work, because the pressure is constant, volume changes. You should note this one. Pressure is constant, but the volume changes. Okay. Therefore, now let's do that. So here you will have that in state, you will have Q in. Okay. And there is no work in is 0. And there is no mass because it is closed system. And therefore, out quantity, you will have that Q out. It is 0 because there is combustion process. And you don't have any, that is, you don't have any volume change here. So sorry, any, that volume, there is volume change here because there is work out, and that one will be equal to P delta V. Okay, because here you can see that pressure is constant, but the volume changes. There is work. Okay. Here you have the boundary work from 2 and 3. You have the boundary work, therefore it is not 0. You have P delta nu actually. And then 3 mass transfer is 0. Okay. And if you write this quantity here, and you will have that Q in will be equal to delta U of the system. Delta U of the system is the second state minus first one, U3 minus U2. Will be U3 minus U2. And the plus that P multiplied with nu 3 minus nu 2. Okay. That is for the, and here you can either write that P3 or you can write P2. It doesn't matter because they are the same. Now this is the Q in. Okay, this is the first law for expansion, first law for compression, first law for combustion. And I should add that here I've said that expansion works. Okay, expansion works. You have one more expansion work here, which is expansion during combustion. So expansion during combustion process. Okay, because here you also have the expansion work. If you remember, I have said that for diesel engines. So this part 2 and 3, this is combustion, but it is also expansion process. Okay. The volume changes, pressure changes. Therefore, you will have also P3 or P2. It doesn't matter. It will be nu 3 minus nu 2, or you can say that P2 multiplied with nu 3 minus nu 2. They are the same. They are the same stuff. But since we are taking work out as positive, this one should be positive. Since now it is positive, no problem. Okay, no problem for our case. Okay, now let me write all of the equations back to here. Now I will write all of the equations back, and you will calculate it and get the final value for me. Okay, now let's write it. So all of the equations. Now, firstly, expansion work. We have two expansion work. First one is U3 minus U4. So U3 minus U4. Okay. Plus the second one, which is P2 or P3. Let me write any of it. It's okay. Nu 3 minus nu 2. Okay. And minus the compression work. Compression work is here. There is a compression work. Let me see. Compression work. Compression work. Yes, it is here. U3 minus U4. No, it is U2 minus U1. U2 minus U1. This is the for compression stage. For the heat addition, you will have that U3 minus U2 plus P P2 or P3, doesn't matter, they are the same stuff. P2 nu3 minus nu2. Okay. And this is the equation. You can replace all of the values and find the final result for that efficiency of the cycle. Okay. So let's finish the problem and finish the lecture. Okay, so let's finish the problem. You can find this one. Okay. Let me show you the values here. You can find values. So this is the formula. You can write the formula, and let me copy the formula here. Okay. So you can calculate this formula here. Then I will finish today's lecture. Okay. So U3 and the U4. U3 value is, let me write them one by one so that you can calculate it. And the U3 value, the internal energy at 3, which is 13 and 16.96, and the internal energy at state 4, it is 520.23. Pressure at 2, which is same as pressure at 3, and that pressure is 6457500. Okay, that is the pressure. And the specific volume at 3, which is 0.073, 0.072, and specific volume at 2, which is that 0.04. This is the specific volume at 2, and the internal energy at state 2 is 675, and the internal energy at 1, which is, go back to the previous state, 216. 260. Okay, now calculate the value here and tell me the final result and finish the lecture. Okay. So let's calculate it, tell the final result, and so this one is false. I've said that this is 0.55. Okay, 0.55% is the efficiency of the ideal diesel engine. Okay, this one is, you should remember, this one is the ideal, but in reality what happens is that, so that the real engine, okay, a real engine has that 3 parts, 1/3, and you have 1/3, and you have 1/3 here. So this 1/3 part, this is the efficient part in real. Okay, this is the efficient part where you get the power. Okay, but the rest, this one and that one, these are losses. Some of this, why do we divide into 2 1/3? One is because is due to friction. Okay, you have the frictional losses because you have the bearings, the rotating equipment inside the engine. Therefore, you have this type of losses. And the next bit of the losses is due to heat loss. Okay. Because you are burning that fuel, and that fuel has combustion energy. Due to it has energy, and that energy is lost as a heat. Okay, you have 2 losses. Okay, and at the end you have the efficient system, which is 1/3. Okay. This is in the real engine. So it is not always 33%. It is 25 to 35%. This is in the reality. Okay. Good. So let's continue and then finish the last part of the question, which says that the map of the cycle. To find the map of the cycle, what we will do is that we say that the work net of the cycle is equal to that map multiplied with nu2, nu max minus nu minimum. So what it means is that in real cycle, you can see in real cycle, the pressure changes continuously. You don't have a fixed amount of the pressure. Okay. What we are saying is that we are saying that there is some average pressure. This is the average. Okay. There is average pressure that when you multiply it with the change of the maximum volume and the minimum volume, you will get the same work. Okay. This is the definition of the mean effective pressure. Okay. And then in our case, that work net was the that numerator of the equation, which is u3 minus u4 plus, let me write it here. So it will be that u3 minus u4 and the plus p2 times nu3 minus nu2 and minus u2 minus u1. And you know the nu max from the chart is, let me see, the nu max value is nu1 or nu4, they are the same. Minimum value is nu2. Okay. This one is nu1 or nu4, and this one is nu2. Okay, you can replace the values and get the result of the method. Okay, so I will not wait for the answer here, but you can work it out. And actually, if you have the values, you can tell me if it is. So you can tell the values if you have it. It will not take a lot of time because we know all of the values, and we have calculated the left part in efficiency, and now only the right part is the problem. So if you can find the result of the mean effective pressure, you can tell me. Okay, so let's see. Does anyone have the? Okay, so you have 206,977. Let me write it here. So the left-hand side is, one person have got it, 206,977. This is the, so 206.998. So this one is joules, yes. So then you should have 206. Yes, okay, 978 kilojoules per kilogram, and this one is joules by kilogram. And this one will be equal to nu max minus nu minimum, and the maximum volume is that. Let me go back to the maximum is nu1, if I have the nu1 here, which is u1 is 0.87 and the nu t is 0.04. 0.87 meter cubes per kilogram, and this one is 0.04 meter cubes per kilogram. And if you divide that value to this one, you will get the, okay, so you will get the mean effective pressure, which will be the average pressure. Okay, this is the average pressure inside the cycle. Okay, you can think of this one, for example, inside the cycle, I've showed you the pressure value change in that manner. Okay, the pressure value change. But we are assuming that there is some average pressure. So for example, this one, P average. Instead of the variations of the pressure values, you take some average pressure. That average pressure is this MEP, mean effective pressure, and it is calculated with respect to change of the maximum and the minimum volume. The result is 249.37 kilopascal. This is the mean effective pressure inside the cycle. Okay, so with this one, I finished the diesel cycle, and now I'm moving on to the next cycle.